Greetings, welcome to back to Smalltalk and Cuis, and what I want to talk about now is AutoMove. And perhaps if we have time, talk about undo, which is also an interesting thing. Uh, so the card table morph is actually the entity that does the AutoMove thing, and sorry, my clock is just chiming. That will be over presently. Uh, and so there's things like a move delay, a number of move steps. So there's some tuning things about how things move around. So depending on how fast your CPU is, you might have cards that zip around, or you may have cards that are sort of stately in their traversal of things. And so you can change the number of move steps, for example, to make them so that for your particular CPU on your device, it's not looking too strange from one to the other. And so here's, I guess this is a shorter one. Animate move from a container to a pile, and then there's some next action which is passed in. And so this is going to be a little trick that has to do with closures and the fact that closures remember their state. So again, this is all computer science. So like in Scheme and various other languages, we have closures which remember their context. And so obviously, there's an animating move to the top card of a pile into a container, and in this case, and so we go through the container and we set the property to of some state information. We find out where the card is in the world, and we transfer the card out of its container, which is all of the containment hierarchy in Cuis is based not in the upper left-hand corner of the screen, which is the world coordinates, but in local coordinates, which is the coordinates of its container. So your XY position, the offset, is the offset in your particular container that just contains you, and that change is made to help us move forward to a totally scalable UI, and we're in process for that. So the container, we have to take the card out of the container. We have to add that back into the world. So the world again is the paste up morph that's the backdrop to the screen, and we want to make sure that we use the proper position relative to the world coordinates. So that's what this little bit of business has done. And now we want to do the animation business. So we want to slide that card to our target position, and we want to go to a morph position in world plus the container offset. So that's just figuring out where we need to go to. We want to do the number of move steps, which you just saw, based on some delay between steps. And then we want to give the card to that other container. So this is our target. So we want to then take the card out of the world. We want to, tell it to, hey, here it is. By the way, here we'll hand this to the particular target, and then we go ahead and do whatever the next action is. And again, the next action is a closure that was handed in at the top up here. And let's see. Do we want to look at that one? That looks pretty much the same thing. Automate move from to. Yeah, I think this just has to deal with a little variance in what the targets are. So slide to end steps delay. Let's just go ahead and take a look at the implementers of this and see if I'm missing something tremendously interesting here. Okay. So we need to slide the card to the new position, and again, this is done using the event system or the timeout. And so other things can happen. This is an asynchronous command. This is using multi-threading abilities. So again, we have the entire bit of computer science in Smalltalk. So we find out what the starting point. We calculate the delta, which is the difference between the start and the end point divided by the number of steps. We say we started with a count of 0, and then when we morph stuff, we evaluate, increase the step count. If we haven't hit the end, then we go ahead and we change the morph position to add in the delta, and we say we got to draw ourselves because we just moved. Otherwise, we're done. So we need to stop stepping. We're at the end. Make sure we're at the end point. We have no more actions in morphic step, and we do whatever the next thing was. So this morphic step is something that is generated by the event system. So how all of this whole bit of business works is that there's an event that goes to the system every time you change, as time marches on, and you do anything. The You get, this is a number of step events. Time is divided up into a number of discrete events, and then everybody's told to change your damage, repair your damage rectangle. When something moves and says, oh, I've changed, I raise my hand, I've changed, all those changes get noted, and then so when the step time comes, it makes a difference, and you see what happens. So that's the basis of stepping. It just sets up a number of steps. Those steps are remembered by a closure, and it goes from, let's see if I can back this up to, okay, here we have some auto moves. So when I come up here, there's some code that just goes through and checks to see if any moves can be automatically done, and if they can, based on some criteria, then it goes ahead, and then we just we go through, and the number of steps is divided up. There's a delta from the start position to the end position. We pull it out of here, take it across the world, and then drop it onto here, and each of these containers knows how to get something added to it. And there's a set of rules about this, but we'll get into rules as a little separate video clip. Okay, so that's basically AutoMove. Let's see. The other bit of business here is, let's see. Yeah, about to be grabbed by. So these get delegated. Dropping and grabbing. So when there's this cute little bit of business when this arrow that you see, the cursor pointer, is a hand morph, something called a hand morph. And actually, let me go ahead and open a browser and show you this while I'm talking about it. That might help. Get a browser, and we're gonna find the hand morph. Okay, so the hand morph, here we are, grabbing and dropping. So the hand morph is able to grab something from the desktop if it allows itself to be grabbed, and there's some checking around that. And for drag and drop, the hand morph acts like a something that is an intermediary between the bride and groom, if you will. the hand morph is fairly simple. It knows how to pick something up, and when it picks something up, that morph stops being owned by its current owner here, and now it's suddenly a submorph, or owned by the hand morph, until the hand morph lets it go, and then it goes and gets dropped on the desktop or wherever it happens to be, based on a couple rules about that. And so how this happens is it creates a drop event, and it finds out who it needs to hand this off to. And if the event was handled, great. And if not, then it says, oh, the morph was rejected, therefore I have to do my cleanup action and like that. And if we take a look at the event itself, so I have to come up and briefly find morph events. That's enough of it. Whoops. Maybe it's morphic event. Maybe I find it right. Okay, yeah. Morphic events. There's a drop event. And this is actually sent to look with the start to finish from no. Yeah, this is what I want. Apologies. So anyway, you're finding how to kind of move around with these things. Oh, wait a minute. Interesting. All right, let's go back here. Apologies. So what happens is first you try to find the morph that contains the mouse point, and then you look through that morph and any of its submorphs until you find one that puts up its hand and says, yes, I take drops. Okay, and so if that morph allows the morph drop, and the morph, the point is actually inside that particular morph is a check, then we take a look, and this I think is actually brilliant. If the morph that you're dropping onto wants the morph that you're dropping, and the morph that you're dropping wants to be dropped onto this other morph, then go ahead and send that drop event, giving the morph in the position. Now, so this is I want her and she wants me. So as I say, and the nice thing about a truly object-oriented system like Smalltalk, you're dealing with objects that know themselves. You're asking them to do things, and they cooperate. And you ask them, say, like deck, shuffle yourself, that sort of thing. And in here, this is really brilliant in that if you're using like a tool environment, and you're saying, oh yeah, I'm taking a drill bit and I'm dropping it over here, and over here might be onto a drill press or a hand drill, which would take a drill bit fit fine. But if you try to drop it onto a blender, a drill bit and a blender just, so it allows for the user interface to be really generic, and you can do any sort of drag and drop behavior with an agreement between the morph that you're dropping, it knows about itself, and the morph that you're, whatever tool or area you're dropping something onto. And so this makes a very nice generic and helpful system. So that's basically so when you're doing that check to see if I like this card to be dropped upon me, you've got some rules, and saying, okay, if let me actually get this out of the way. So if I take a card here and try to drop it here, that doesn't work. Because the rule of having one more than this card is in the same suit is invalid. And same thing over here, but if I drop a 4 of hearts and a 3 of hearts, the container knows to look at its top card and that we have another card of the same suit that's one higher than the card that's currently there. And so that's helpful to us. And even the same checks are going on here with the AutoMove and stuff, where it just goes and looks from all the possible places that a move could come from, and does those sorts of things. Sorry, these games are addictive. Okay, so that is that. Oh, that's what I was going to show. I was going to show you drop shadows, but I think I'll save that for the next segment and call that good for the moment. Okay, see you next time. Hope you're enjoying this. I am.